Okay, now we're going to dive a little deeper into our Lewis structures. And we're going to look at the Lewis structures for polyatomic ion molecules. These are molecules such as ammonium, your NH4 molecule, which has a 1 plus charge, or something like sulfite, SO3, with a 2 minus charge. You know these from our ionic naming, but those ions are actually themselves molecules. So let's start with the ammonium ion, NH4 with a 1 plus charge. This molecule has 1 nitrogen and 4 hydrogens. So if I were to add up the number of valence electrons, what I would see is that we have 5 valence electrons for the nitrogen, and each of the hydrogens have 1 valence electron for a total of 9 valence electrons to be shared in this molecule. But you have to remember this is a +1 charge, which means that at some point this molecule must have lost an electron because it became 1 positive. So that means we have to deduct 1 electron from the total number of electrons in this molecule for a molecule that will have 8 electrons now in its bonding. The rest of the process is basically all the same. We start by doing a single bonded structure with nitrogen in the center because nitrogen needs the most electrons and it can never be hydrogen in the center. Each of those 4 bonds has 2 electrons, so we deduct 8 electrons from the total. We have no electrons left, and now we have to check, does everything have an octet? Well, that hydrogen has an octet because it has 2, 2, 2, 2 for each of the hydrogens, and the nitrogen has 8 because it has 4 bonds. The last little quirk that we do for ions is we put them in brackets. Say this whole molecule has a 1 positive charge. It is not neutral, it is an ion. Now let's do the same thing for SO3 2 minus, which we know is this sulfite ion. Sulfite has 1 sulfur with 3 oxygens, all of which have 6 valence electrons, for a total of 24 valence electrons. But since sulfite has a 2 minus charge, we have to take that into account. A 2 minus charge means that the molecule has gained 2 electrons. So we have to add that to the total for a total of 26 electrons in our bonding structure. Again, just like before, we do a single bonding structure, having sulfur in the middle because even though sulfur and oxygen all need 2 electrons, sulfur is less electronegative than oxygen, so it goes in the center. Those 3 bonds use 6 electrons, so we deduct them from the total. Now we have 20 electrons remaining to add to the bonding structure. We add them first as lone pairs to the exterior atoms first, and filling the octets of the oxygens on the outside uses up 18 electrons, so we deduct that from the total for 2 electrons remaining. Those last 2 electrons go in the central atom, and we check to make sure everything has an octet. This oxygen has an octet, this oxygen has an octet, this oxygen has an octet, and the sulfur in the center has an octet. We are done our structure, except it is an ion, so once again, we put the entire thing in brackets and say it has a 2 minus charge. Now let's do one more structure, our carbonate ion. Now, this one's going to have a new wrinkle, a wrinkle that we call resonance, which I'll explain what that means when it gets there. But first, let's just start off like normal by adding up the number of valence electrons in the elements in the molecule. Doing so, we see that the molecule has 22 electrons. But wait, again, it is an ion with a 2 minus charge. That means it gained 2 electrons. We have to add those 2 electrons to the charge, to the molecule to say there's 24 total electrons in our bonding structure. We once again start off with the carbon in the center and the other atoms surrounding it, all single bonded, and we deduct the 6 electrons used to make those 3 bonds from the total, and now we have 18 electrons that have to go into the structure. Filling the octet of the exterior oxygen atoms, we see that we use all 18 of those electrons and we have none left over. Now we check to see if we have an octet everywhere. This oxygen has an octet, this oxygen has an octet, this oxygen has an octet, but the carbon does not have an octet. So what do? Well, it turns out, just like in our other structures, we have to take a lone pair and swing them in to make a double bond. By swinging in that lone pair from the one oxygen to the carbon, now what I've done is I've increase the amount of electrons available to the carbon so that it has an octet, but this oxygen still has an octet because now it has 4 bonded electrons and 4 lone pair for 8 total. Why did I choose this oxygen to take the electrons from, leaving these oxygens all to have 3 sets of lone pairs? Well, it turns out when we actually look at these molecules with instrumentation, none of those oxygens are single bonded to the carbon, and none of them are actually double bonded to the carbon. It's almost as if each carbon-oxygen bond is a 1 1/3 bond, which is kind of a weird thing, and it's not possible for us to draw. So what we draw is this thing called resonance structures. Resonance structures shows that that double bond is actually split among all 3 of the oxygens. And the way that we represent that in a drawing is not by just drawing out one ion like I have here, but actually drawing 3 possible ions that all contribute to the overall structure, like this. And these 3 structures show that the double bond does not exist between just this carbon and oxygen in the molecule, but it also kind of exists between this carbon and oxygen in the molecule, and also kind of exists between the 3rd carbon and oxygen in the molecule. In fact, none of these bonds are single bonds, and none of them are double bonds, and they're all about 1 1/3 bond. And the way we show that is by drawing all 3 structures and showing the double bond moving throughout the molecule. This concept is called resonance. And again, we know this to be true because when we look at these molecules with instruments and measure the bond strength, we see that that bond is not a double bond, not a single bond, but exactly what we would expect of a 1 1/3 bond.